So, hope that's clear. Now, we have one more problem, number 10, dealing with the same type of situation. Okay, light of wavelength, let's see, wavelength of 211 nanometers, that's way in the ultraviolet, is shown onto copper. That's the photon, and the work energy of this copper is 4.94 electron volt. What is the maximum kinetic energy of the electrons that are emitted? So these electrons are kicked off, and the question is, what is the kinetic energy of the electrons? So remember, the kinetic energy, the energy of the electrons kicked off, is equal to the photon energy, the energy of the photon, minus this work function. Okay, so the energy of the photon comes from here. The energy of the photon is h times the frequency. Now we have the wavelength though, so it would be, remember, frequency times wavelength equals c. So wavelength equals c divided by frequency. So I'm going to substitute here h c divided by frequency minus the work function equals the kinetic energy of the electron. So I'm going to plug into here. Okay. H is 4.14 times 10 to the minus 15 electron volt times second. Speed of light is 3 times 10 to the 8th meters per second. And the frequency, I meant to say, you know what I meant to say? I meant to say that the frequency is c over lambda. That's c over lambda. Sorry about that. Because we don't have the frequency, but we have lambda. So I wanted to substitute for frequency. I did it wrong. Okay, and I'm going to put in the lambda is 211 times 10 to the minus 9 meters, and I subtract then the work function to 4.94 electron volt. Okay, so this first term here is 4.14 e to the minus 15 times speed of light, times speed of light divided by the wavelength. Okay, and I get 5.88 electron volts. That's the energy of the photon, and I had to subtract the work energy. And I get a kinetic energy of 0.94 electron volt. So the electrons would come off with this amount of energy. Okay. Well, I hope you have you've done well with these problems, and there's two main issues here with this chapter. Is dealing with the velocity of sound and the Doppler shift, and then we switch completely over to light waves, dealing with Planck's law, Planck's constant, and this work function in Einstein's photoelectric effect. Well, all right. right, that ends these practice problems for Chapter 11. We're now going to do, for the next little video clip will be on the overview of the lab. Well, hello. This is the lab overview for Module 11. And this lab actually has two parts to it, and what you'll receive, the lab looks something like this. Don't know if you can see that, but there is an oscilloscope on the first page, and it's a rather thick lab, unfortunately. Sorry about that. But there's so much two waves that there's a lot to go over, and there's two articles that you will see attached to this. One is called The Speed of Sound Using Lissajous Patterns. It's a short article from this. Actually, it's from a magazine called The Physics Teacher. It's an excellent article. And then there's another article. It's called The Guitar. And it's with this little lady playing the guitar in the front. But if you look at it, it goes over the physics and the waves and of guitars, and it's all about string and the harmonics and what it looks like. So these are two good articles that you actually need to go over for the lab. So this appears to be at first a rather lengthy lab, but well, and it probably is a lengthy lab. Okay, the first part of the lab is first getting familiar with the oscilloscope. The oscilloscope is a device where it's a cathode ray tube, and this is a screen. This is a front screen, and if I put, and there's what we call a there's different channels, but in particular, if I put a signal, a sinusoidal signal, say like a microphone with a whistle, this time, when the sound wave hits the microphone, this is a microphone, and that signal goes into the oscilloscope, that becomes basically what happens is the electric signal from here causes the trace on the oscilloscope to go up and down, and then there's a time sweep. There's a time sweep across, and you end up getting this signal like this. The signal, the electron beam sweeps across the oscilloscope, and it tracks the exact nature of the wave exactly as recorded by the microphone. Well, there's another way you can hook up the microphone, the oscilloscope, and that's where we have what we'll call a signal is applied to the horizontal, and the signal is applied to the vertical. Now what happens here is the beam is put in a different mode, and the beam just sits right in the center of the screen. So the electron beam just simply, there's no time base here, this electron beam just sits right in the center of the oscilloscope. And if I put a horizontal signal to the scope, to the oscilloscope, in a horizontal mode, this beam goes back and forth horizontally. Now if I put a completely different vertical signal on the beam goes up and down vertically. Okay? So if I put a sine wave on here, like this, the beam will go back and forth, just like a sine wave. And then if I put a sine wave on the vertical wave, on the vertical portion, it goes back and forth like this. Well, if these things are perfectly aligned right, the two beams will end up going like this. They'll go, these two beams will go up and down, up and down. And what you trace out is a perfectly horizontal, a slanted line. Okay, a slanted line. That is when the beam is over, when the horizontal portion is over here, when we're over here at this point, we're up here, and this beam tracks on a 45-degree angle, and it perfectly tracks like this. Well, if we start to shift the phase, if these get out of phase, suppose if they start getting out of phase, that is, this one normally would start here, but it starts somewhere down here. Okay, then it gets out of phase, and what we start to generate is a pattern that starts to track what's called an elliptical orbit. Elliptical orbit. Okay. Now, when it's 90 degrees out of phase, okay, it actually becomes a circle. And if you look on page 4 here, I'm skipping a little bit here, but if we'll come back to it. If you look at page 4, if these two signals are 90 degrees out of phase, what you see on the oscilloscope becomes a circular pattern. So it starts out as, if they're perfectly in phase, it starts out, if, in other words, there's a phase shift. If this y here, let's see, if the x here is a certain signal, some amplitude times a cosine, and then if the y here signal is the cosine, it's the same, plus there's a phase shift. This is a phase shift. Okay, now I haven't even talked what about the omega t is, but I'm probably getting too much ahead of myself here. But let me just say, the phase when the phase shift is 0, look on page 4. Okay. When the phase shift is 0, actually I think I may have just drawn wrong. When the phase shift is 0, the line will be like this. When the phase shift becomes 45 degrees, it becomes more elliptical. When it becomes 90 degrees, it's a circular pattern. And when it becomes 180 degrees, it's completely add up. I think I have this drawing. I'm going to redo it and make sure it's right. In any case, so the phase, by seeing the pattern here, you can see what the phase shift is. Well, what is this omega t? Remember, omega here, I think we've had this before. Omega is is called angular frequency. Okay, angular frequency. And remember, it's 2 pi f. 2 pi f, or it's the same thing as 2 pi divided by the period. Okay. So, so basically, if we would rewrite this signal, it would be the amplitude times cosine of 2 pi times the frequency, and I can say it's 2 pi over the period times t. So notice I have a t divided by the time divided by the period. So if t is 0, if t equals 0, we just have cosine of 0. Cosine of 0 is, of course, 1. Okay. If t is equal to big T, then this becomes t over t, and we just have cosine of 2 pi. Okay, because t divided by t is 1. Okay, so whenever so basically, if we have the cosine curve, we go through one cycle, and here's 2 pi. Okay, and from a period point of view, if that t from here, if this is equal to 1 period, then that's one whole wavelength. This is from an angular point of view. This is 2 pi radians from here to here. The next, okay, if time continues, this will be 2t. Okay, and if this is a 2t, then what we have is we have the cosine of 4 pi, which is the same thing as the cosine of 2 pi, and we're back up to here. So you can kind of see how this goes. Now, what is this? The experiment actually is going to be is measuring the speed of sound. And the way, it's a very slick experiment, and the way we're going to do this is with the setup shown on page 2. We have 2 microphones, and we have a speaker. And the speaker emits a certain frequency. Okay? And we have a electronic generator that's hooked right up to the speaker. Okay, so that emanates a sound. Okay, and actually, there's actually one. Well, let me say this. What we're going to do before I draw one. Well, we have one microphone. What we're going to do is we're going to take in, for our inputs into the oscilloscope, what's being driven into the speaker goes into the vertical. Goes into the horizontal. Okay. Actually, I will show that going into the horizontal this way. Going into the horizontal portion of the oscilloscope, and the microphone goes into the vertical. And what we do is we arrange this so that we move this back and forth, we move the microphone back and forth until we get a nice line right like this. Okay. And then once we have one line established, we mark that location, and we move the microphone down a little bit distance, and we measure what this distance is. We move it such that this this Lissajous pattern, this is called, I didn't explain this very well, but this pattern that's generated here is called a Lissajous pattern, it's a French name, Lissajous figure, named after some French person who discovered it, basically. So when we move this down, this pattern will go from here to 180 degrees, out of phase, and then back. So we'll go through one complete cycle. So this distance from here to here will go through one complete cycle, Lissajous cycle, and so that represents one wavelength. One wavelength from here to here. And we know it's a wavelength because we can see it, we can see this pattern shift one complete wavelength. Okay? So if we know what the frequency is, and we can measure the frequency, and if we know what the wavelength is, and we can measure the wavelength, we can get the velocity of sound. Okay? So it's a very simple experiment in this regard, but it requires an oscilloscope, generator, a microphone and a speaker, and we know what the frequency is because we measure with the oscilloscope. We know what the wavelength is, multiply the two together, and we can calculate the speed of sound. Okay, so that's the whole point of this portion of the lab. So if you look over on page 3, there's some information there dealing with cosine waves and sine waves. Go through that. And on page 4, there's a diagram dealing with what we're dealing with here, the phase shift. The actual measurements, okay, are done, and we take the measurements here, and all the data is collected on page 5, where we measure. The first thing we do, okay, is we take the signal generator and we put it into the oscilloscope, and we measure one complete period. And if we know what the period is, remember that the frequency is 1 over the period. So we switch it to where we have the oscilloscope in time-based mode, and we measure the actual wavelength of this frequency here. And so we can actually measure what the frequency coming out of the generator is. So so we measure the oscilloscope. On the oscilloscope, the period in seconds, in milliseconds. We measure it in milliseconds, we convert it to seconds, and from that we can calculate what the frequency is. We measure what the wavelength is from this arrangement, and then we can calculate the speed of sound. Okay, and we're doing this roughly at room temperature, or about 70 degrees or 21 degrees centigrade, and so you can then calculate what according to theory, what the theoretical velocity should be in terms in meters per second. Okay, and page 6 there's some more questions on page 6 to perform, and on page 7 for extra credit, I want you. This is a tricky thing to do, but go through here if you're willing to do this. And it's an excellent problem, but it takes some effort, is to apply a sinusoidal wave to the horizontal and to the vertical, and go ahead and use the signals. For the signals, what I want you to do is to use, say that the horizontal is A cosine WT, and say that the vertical is A cosine WT plus theta, just the phase difference, and go ahead and mathematically derive what this Lissajous pattern is. Now, you may not even know exactly how to start doing this. It's a difficult thing to do. All you need is algebra. Doesn't require any calculus. Essentially, the way to think of it is, if you want to do the extra credit problem, the way to think of it is this. Let this signal be your x, and let this signal be your y. Okay? So essentially what we're trying to do is to find the shape of a curve if when the x is given by this and the y is given by this. Sounds easy enough, but mathematically it's a little bit tricky. You need to take these two and combine them in a certain, basically you combine the x and y term in order to be a function. Okay, I'll let you struggle with that, and maybe I'll give you some tips on that to kind of get you going. But let's continue. Okay, on page 8. On page 8 of the lab, we're going to do a completely different kind of experiment. It's still going to use sound, but this is where we're going to take a guitar string, and we're going to pluck a guitar string. We're going to take, I have a stand, a wooden stand. We take a guitar string, here's a guitar string, and I use a pulley, and I put a certain weight on here. Now the weight acting down puts a certain tension right here. There's a certain tension on the string. With a certain tension on the string, and you know just from a guitar, when you pluck the string it goes boing, right? And the more weight you add, the higher the tension, bang, bang, the frequency goes up. Okay. Well, how does the frequency go up? Well, if you, that's the purpose of the other paper, little paper that I give you. And basically what this says is that the velocity, okay, that the velocity of the wave traveling down the string is equal to the tension divided by some constant, with this square root of a tension divided by some constant. And this constant, mu, right here, this T here, this T is a tension. Remember, that's a force. Okay, so the weight here will be the tension. This mu here is the mass of the string per unit length. Okay, so it's like the kilograms per meter of the string. So it's going to be for a string, this is it's going to be a small number. Okay, so what do I want you to do here mathematically? What we're going to do is we're going to go through here, and what happens when you pluck the string, a wave sets up, and when you pluck the string, okay, the first fundamental wave that sets up is, notice, this end of the string is fixed, and this end of the string is fixed. So the wave, the first fundamental wave that sets up, is where you have a wave that the string vibrates like this, up and down, and it's tied here and it's tied here. Well, what does that look like? What that looks like, if that's one wavelength, if it's tied here and it's tied here, this distance is 1/2 a wavelength. Okay, so when you have a string that's plucked, that's tied at either end, the fundamental what's called the fundamental frequency is such that the wavelength, the half a wavelength, goes from end to end. Now, you can also have what's called harmonics, okay, where what can happen is, now we're not going to deal with harmonics today, but basically in a harmonic situation, if this tied here, this represents the fundamental. In our harmonic, you can get more. Okay, where this is the first harmonic, you get twice the frequency. Okay, where the string vibrates such that there's a node right in the middle. That would be the first harmonic. The second harmonic would be, whoops, where there's two. I didn't draw it very well. Okay, where this third harmonic is 3 times, this is a fundamental, second harmonic